Good morning. Can you hear me now?
I see you're still breaking up.
Can you hear me? Okay, can you hear? Let's continue. So this was to meet with this topic. Okay. So I think I was at instantaneous speed. So what I said, actually I've already discussed this. I wanted to introduce the derivative. Okay. Still a lot here. So introduction of the derivative. So we are focusing on approximating and calculating the derivative. We see that the slope of the tangent line of y equals to fx at the value of x, where the x can be approximated by a slope of a secant. So here basically what you are explaining here is that let's say we have this curve here. So this is y, and so at this point here is p, and here is q. So to find this slope here at p, you basically what you are doing, you are approximating this point here. We can make it x, and that point, at that point you can make it and maybe x plus h. So now you take the limit of a quotient difference as x approaches h, fx plus h minus fx all over h. So, and if you check here, this point here on the y, it will actually be your fx, and that point there on top there will be your f at x plus h. So now you are using these 2 points. It's like in high school where m is equals to y2 minus y1 over x2 minus x1. So this is your y values, and this is your x value, and this is your x value. So this, I know you know the first principle. So basically this is equals to the derivative. So this is f prime of x is equals to this. Okay, again, I still have another clear graph here below. So basically what they are saying here is that at this point and that point, this is the secant. So you are actually approximating the slope, the derivative using the slope of a secant. So this is our secant. This point here is our P, and this point is our Q. So like I said, we'll end up with f prime of x equals to the limit as x approaches h of x at x plus h minus fx all over h. Now, because now we know this equation of calculating the limit, now we'll first use this equation, which is called the first principle, to calculate our derivative, and then we move to the standard derivatives. So here again, this graph is still explaining the same concept, that we are actually approximating this slope. This is the slope of a secant PQ to determine the derivative. Okay. Now, as the value of delta x increase, it will reach the point x. When it reaches the point x, then there we can say that f prime of x, because we know that m, the gradient, is equals to this, equals to the limit as x delta x approaches 0 of f x plus delta x minus fx all over delta x. So this gives us the derivative. I'm just highlighting that. So basically that's what they're explaining here. Now the formal definition. The derivative of fx at x is given by f prime of x equals to the limit as delta x approaches 0 of f at x plus delta x minus fx all over delta x, provided the limit exists. So there are times when the limit does not exist. For all x for which this limit exists, f prime of x is a function of x. Okay. Now here are the activities. The activities will try to summarize what we have done, starting from the average. You see here they say calculate the average of change. And here what are they looking at? The average velocity. And on this one, these two, I think they are looking for instantaneous velocity, both two. Okay, so let's do this activity. I think there's somewhere where I was practicing. Okay, let's start with number 1. I hope you have copied number 1. One note, just to illustrate, because you can end up getting this type of questions. We are given kt is equals to the square root of 3t plus 1. Okay. Now we want to determine the change. What was the question there? I want to be clear. Average change. Okay, I don't know how I'll write it out, and let's just use average. Average. Okay. Average kt. Let's just move. It will be equals to k t2 minus k t1 all over t2 minus t1. And they said here t2 is equals to 5 and t1 is equals to 1. So substituting here, we have the square root of, if you substitute 5 here, it will be 16 minus the square root of, we substitute 1, I think is 4, all over 5 minus 1. And this is 4 minus 2 over 4. This is equals to 0.5 unit. Okay. So now the second one, they say a particle is traveling along a straight line. Its position at the time t is given by s equals to 2t plus 5. Find the average velocity of the particles as t changes from 0 seconds to 4 seconds. So you must be careful. This is st. So if it's st, this means it's different. It's not average. Okay, I think is it average velocity? Average velocity. So here we are given st is equals to 2t squared plus 5. So how do we relate velocity to distance? And they said t is what? T is equals to to 4, and t is equals to 0. So this means you can use the formula for instantaneous velocity. So you'll determine the limit as t approaches. Where is that formula? I was not supposed to do these complicated things. For instantaneous velocity. Okay, so this is the type of formula that you're going to use. So we have to design our own for average velocity there. So this will be S at t plus delta t minus st all over, I think here it must be change in t, 0. So this is change in t. So this is the same equivalent to a shortcut. I'm not going to do this in detail because it wants a first principle, which we are still going to do. This is 4t, and then if you look here, we start at 4. This the difference, 4 minus 0 there is 4. So our answer here will be 4, and 4, this is equals to 16 units. The unit, I think, will be meters per second. Okay. So another thing that you must be aware of, the first principle is not examinable. So we don't have to ask you a question from the first principle. We use it to introduce you to the standard derivatives. So most of the part that I'm doing here, they're not examinable. It's just a way of introducing the derivatives. So we'll do similar thing for this one. We see it's a distance, then we have to differentiate this guy. ds dt is equals to 10. Then you have to find the velocity of the particle at 4 seconds, then you substitute, they will end up with 40. And here they say you are looking for instantaneous rate of change, so you have to use the formula for instantaneous rate of change. So for this one, because you have to write it in terms of k, let's see how we can write that. I think it's going to be g of k plus delta k minus g k all over change in k. So here the limit as delta k approaches 0. So I'm just rewriting this one in terms of k. Then work it out there. So, but the shortcut, you can see that is the same as 4k plus 1, then you substitute 3. So here we end up with 4 plus 1. This is actually 17. Okay. Now, these activities are important. Here, this is called what? Quotient difference. This formula here, they ask us to determine that. But if you look at it closely, it basically prepares you for the first principle. Okay, if we check, immediately after that, they say that you determine the first principle, determine the derivative from the first principle. So we have two options. You can do it directly. Maybe we can jump this one and just go directly to the first principle because these two are related. Okay, I think we should focus here. Let me solve some of these problems, not all of them. Okay, now which one can I do? Just to remind you about the first principle. I don't have to do all of them. You can choose 2 or 3. Hello, are you there?
Say, do questions 6 and 5.
6
and 5.
6 and 5. 6 and 5, they are related. Why don't you just take one?
Say 6 and 4, say.
6 and
4 and 6. Okay.
Yes.
So let's start with 4. So what we are going to do here, we know the formula. We are given fx equals to x to the power 3. Now fx plus h, so let me highlight that this is number 4. Fx is equals to x plus h to the power 3. So I usually find a way of simplifying my this. So you remember that we have been using Pascal triangle at some point. So we can take advantage of that. So it means that here the coefficient will be 1, 3, 3, 1. So this will be x to the power 3 plus 3 x squared. You can see that x squared is decreasing plus 3x plus h to the power 3. So I left h intentionally. So you can clearly see that here we'll have h to the power 0, h to the power 1, h to the power 2. So you can see that h is increasing and x is decreasing. So now I'm going to write it clearly. So that was an explanation. So this means this is x to the power 3. I want to avoid this h to the power 0. X to the power 3 plus 3 x squared h plus 3xh squared plus h to the power 3. Now we want to determine f prime. F prime of x is equals to the limit as x approaches. I'm used to x. The limit as h approaches 0, but I can clearly see what there's something wrong. X plus h minus fx all over h. So this is h. So this is equals to x to the power 3 plus 3x squared h plus 3hx squared. I can just write it like that. Plus, let me write it clearly, xh squared plus h to the power 3 minus x to the power 3. Now, all over h. And the rule is that the limit, you must always keep the limit as h approaches 0. Now, you can clearly see that this guy cancels this one out. And then on the next step, what do? We take h out as a common factor. So we have the limit as h approaches 0. We take h out as a common factor. This is 3x squared plus 3xh plus h squared all over h. So h and h cancel out. So what do we have? We have the limit. Let me copy it first. As h approaches 0 of 3x squared plus 3xh plus h squared. Now we substitute wherever we see h, we substitute h. So we'll remain with 3x squared. So this is equals to 3x squared. So this is our answer here. So this means the derivative of the derivative of x to the power 3 is 3x, is x squared. In shorthand notation, so that we can remember what we were doing here. So this is our answer here. Okay, I know this type you've done it in high school in detail, so it's required here to introduce it. So I'm going to do the last one that you have asked, number 6. Where is number 6? There's somewhere where I've scribbled part 1. Okay, number 6, I think we have x over x plus h. Okay. I'm thinking on how to approach it. So this means this is equals to fx. So I just need to determine fx plus h. So this will be x plus h over, there's something wrong. That's why I was thinking, is this x plus h or what? Let me see. X plus 1. So x plus 1. So this one, the third one is okay. So this will be x plus h plus 1. Now I'm looking for the limit. Can you, I can see there's a problem. Okay. I think now it's fine. So I'm going to start this problem again. On number 6, we are given x over x plus 1 equals to fx. Now I'm determining f at x plus h, which will be equals to this. Now let me write it in detail nicely. We are looking for f prime of x, which is equals to the limit as h approaches 0 of fx plus h minus fx all over h. So now I'm going to substitute this guy here and this one. So we have x plus h over x plus h plus 1 minus x over x plus 1 all over h, and then here we have the limit as x as h, I'm used to x as h approaches 0, so bear in mind for me there. Now because of space and what, so these are two fractions. I'm going to use the lowest common denominator. So the lowest common denominator, we multiply our denominator together, okay? So we have the limit as h approaches 0 of what? Of x plus h multiplied by x plus 1 minus x multiplied by x plus h plus 1 all over h multiplied by x plus h plus 1 multiplied by x plus 1. So it simplifies to this. I don't know if you get it. Now the only thing that remains is for me to simplify this expression. So we have x squared. I'm taking off the brackets, x squared plus x plus xh plus h minus x squared minus xh minus x all over h multiplied by x plus h plus 1 x plus 1. Now if you look at this one, we are looking for the like terms. X squared cancel x squared, x plus h cancel this one, this guy cancel this one. Now what is remaining there? We are remaining with the limit as h approaches 0, on top we have h over x plus h plus 1, x plus 1. Now we have h below, h and h cancel out. Now we have the limit as h approaches 0, 1 over x plus h plus 1 all over x plus 1. So now if we substitute h equals to 0, we end up with 1 over x plus 1 squared. So this is our derivative. Now, this problem also, you can check it using your, I don't want to introduce complicated method before you not. Okay, so you'll record this. Maybe later once I have introduced the method called quotient, for those who are from high school, quotient rule. So once I have introduced this method, you can ask me to go back and check if this is the answer. Okay, but this is the method I followed to solve this problem. The other one that I can think of, maybe for interest's sake, I can think of another one. In high school, this one, fx maybe equals to the square root of, let's say, x squared plus 1. And I ask you to determine this one using the first principle. So in this case, it's going to be f prime of x equals to the limit as h approaches 0 of f at x plus h minus fx all over h. And this one, you can write this guy here to be equals to the square root of x plus h squared plus 1. So immediately after that, you substitute the limit, and this one actually will be easy for you because we have rationalized before. So this will be x plus h squared plus 1 minus the square root of x squared plus 1 all over h. Okay, now for you to be able to solve this type of problem, we need to use the method of rationalization. So you'll multiply the top one. You see here, we look for the conjugate of the top one. So basically what it means is that if I do this in detail, so we end up limit as h approaches 0. So here we have x plus h squared plus 1 minus the square root of x squared plus 1 all over h multiplied by the conjugate. The conjugate is x plus h squared plus 1 plus the square root of x squared plus 1 all over the same thing, the square root of x plus h squared plus 1 plus the square root of x squared plus 1. So this is equals to the limit as x approaches 0. So from our experience, we can see that the top one is actually the difference of two squares. So it will be the same as if you multiply the first one and the last ones. So we end up with x plus h squared plus 1 minus x plus 1. This is squared plus 1. I'm doing it mentally, so you have to do it thoroughly. So this is h. So the top one we just copy as it is. The square root of x plus h squared, we squared this plus 1. Usually I don't have the denominator to simplify itself out. Okay, now you can clearly see now we need to expand the top part. So we have the limit as x as this is h where root x
Sir, you're cutting again.
to x. Okay, we have to expand this. This is x squared plus 2x. Motaung, can you hear me? Otherwise, I must cancel the class. So, can you hear me? Musima?
Yes, sir. I can hear you.
Okay, so let's complete this problem here. Hey, this is a problem, this network thing. Okay, I'll fix that for the next class. Plus x squared plus 1 plus the square root of x squared plus 1. We close this bracket here. So here, what I wanted to show you, we have like terms. This guy here cancel this one. 1 cancel minus 1. We take out the common factor. So we have the limit as h approaches 0. And we take h out as a common factor. You have 2x plus h all over h and the square root of x plus h squared plus 1 plus the square root of x squared plus 1. So h and h cancel out. Now if you substitute h wherever you see h here, you end up with 2x over 2 the square root of x plus 1. And then 2 and 2 cancel out. We have x over the square root of x plus 1. Okay, so this means we have managed to solve this problem. That's the answer. So there's a shorthand methods that you are going to use, but it's important that you can be able to read this and be able to solve this type of questions. Okay. Now I'm going to go back to my notes. Now the last thing that we have to discuss is the relationship between differentiability and continuity. In the previous classes, we have discussed continuity. Now here, the most important is the differentiability. How are they related? Okay, so I'm going to summarize it in short. For a function to be differentiable, it must be continuous. Okay, that's the short statement that you must always remember. For a function to be differentiable, it must be continuous. So an alternative limit form of the derivative shown below is useful in investigating relationship between differentiability and continuity. Okay, so this is another type of determining the derivative at C. Okay, provided the limits exist. Note that actually this thing is the same. It's just that here they've just substituted C, but it's fine. We note that the existence of the limit in this is an alternative form of we note that the existence of the limit is an alternative form that requires that one-sided limits must exist. So here, if you are given this type of problem, you have to check the limit from the left and check the limit from the right. And these two, they must be equal. And if they are equal, then we can conclude that the limit at that point exist. Okay. Now we are still under differentiability and continuity. It follows that f is differentiable on the closed interval AB when it is differentiable on an open interval. So what they mean is here is that if you have, let's say, a rough sketch here, let's say we have this function here. So there's a point A here and a point here, B. So the first one, it means that A and B is included. And the second one, it means that A and B is excluded. So if your function is differentiable at an open interval AB, then we conclude that this is also differentiable on this closed interval. Okay. Now the last part, it means that differentiability implies continuity. So wherever you are able to differentiate a function, it means that that function that is given to you, it is continuous at that point. So let's say if I give you fx equals to x squared, and then I say differentiate this function at x equals to 9. So you determine the derivative at is equals to 2x, and substituting that, this means f prime at 9 is equals to 18. So the fact that I was able to determine the derivative at a given point, it means that a function, this f equals to x squared, it is continuous at x equals to 9. But now the problem is that the converse is not always true. The converse is when you rewrite this one. It means that a function that is continuous at C is not necessarily differentiable at C. So you rewrite this one, you start with continuity. A function, when we do the converse, the function that is continuous at C is not necessarily differentiable at C. So then I have an activities that will show you that this is the case, okay? Now, let's see, for example, this say use an alternative form of derivative to find the derivative at x equals to C. So here my C is this guy here. I'll take the advantage that you have done maths at high school. For this one, the derivative here is 3x squared plus 4x. Now substituting minus 2, you can see that this will be 4 times 3 is 12. 12 plus 8. So this is equals to 20. So for this one, you can clearly see that the derivative exists at C. Now, if we use that form that they asked us to use, the limit as x approaches minus 2 from the negative side of fx, and then it must be equals to the limit as x approaches minus 2 from the positive side of fx. So we can clearly do that. So now the formula, I want that formula, it seems like I wrote it wrong. Minus fc. So this is minus fc here, minus fc all over x minus c, minus fc here, all over, this is c, over x minus c. So these two must be equal. For what? Let's see, for the limit to exist. Okay. Now let's check. Let's check now if we get the same answer. Okay. So for the first one, the limit, the answer here will be, remember these two are equal. This guy here at minus 2 is equals to 1. And this guy at minus 2 is from the positive side is also equals to 1. Okay, I'll explain why I say so. The best way is to use the graph. I'm going to use the graph to explain the concept. I'll plot the graph for you. Or you can calculate the derivative then. And I think this minus 20. Please check if I've done everything correctly here, because the correct answer I think must be 1, not 20. I don't know what I've done there, but I'll explain it using the graph. Okay, you are given x to the power. I'll enlarge it for you to see what's going on. Let's just use 300. X to the power 3 plus 2x plus 1. So this is the function that we are given. Okay, let's see. This is okay. Now, if we were to plot this graph, okay, comma, plot range. Let me change the range. So you can clearly see the graph. Okay. Now, at -2, I think -2 is this point here. Our slope, what is our slope at this point? Oh, so you have to calculate the slope. So in that case, we got 20. I think it's correct. You calculate the slope, then you see that. But now you can clearly see that from the negative side, from this side. Let me highlight this. See if it's a PDF. Is it possible? Okay, so that I can write on it. Where is it now? File, save as. I want it on the desktop. Okay, let's just discuss that and see. So this is the graph that we have plotted here. So what I wanted to highlight, we'll check the derivative is correct, that one. If you approach this function from this side that of -2, this is our -2 here, and you approach it from the positive side of -2. The question is, are we approaching the same value? If you approach the same value, it means that our limit will be the same, physical concept of a limit. Okay. So on the first one, where is that one? The first one, this one, our limit will exist. Okay, using this form of the derivative, it will exist and equals to the same value. But now the problem will arise when we calculate this one here. Okay, the absolute value of 6 at 6. Okay, I'll do it mathematically first. Let's do that. So we have the limit. So remember, our function is fx equals to the absolute value of x minus 6. So we have the limit as x approaches c of x minus 6, this one. How do you write this one? Yeah, I think this is correct. Okay. This is fx minus fc all over x minus c. But in terms of this one, they said my c is equals to 6. Now I want to write it in this form. So it's going to be the limit as x approaches 6. And then here we have x minus 6 minus, now at 6, this is 0, all over x minus 6. Okay, so this is what it resulted. So to solve this problem numerically, it will be very long because we know the absolute value is equals, I can write it as plus or minus the square root of x minus 6 and solve. I'm going to use a sketch. So mathematically, it's always easy to use a sketch. Now, absolute value of x minus 6. Let's see what does that gives us. And then we plot that. So this is the graph. Now here we are interested in the slope. So the slope this side, if you look at this point here, let's save. That we can discuss, we can just give it a name, absolute value. Is fine, that one. So we'll solve it there as a PDF. So that we'll be able to write on it. So if you look at this one here, I wanted to explain that concept again. So in this case, you check the slope. So the slope here, this point here is 6 and 0, and this point here is 0 and 6. So calculating the slope here, what is your slope? And this one here also, what will be the slope of this one? Let's start with this one. M equals to, if we make this one your y2, this will be your y1, x2, x1. So it will be 6 minus 0 over 0 minus 6, if I'm not mistaken. So the slope is minus 1. And the slope of this one will be m equals to 1. So you can clearly see that the limit as x approaches 6 from the negative side, we solve that one to be x minus 6 over x minus 6. This guy is equals to negative 1 from the left hand side, and the limit as x approaches 6 from the positive side, this is what we got, over x minus 6, this is equals to positive 1. So these two are not equal. So our conclusion is that if you look at the graph, you can plot this graph without lifting your hand. So this function is continuous. It's a continuous function. But the problem is that this function is not differentiable at x equals to 6. The derivative doesn't exist at x equals to 6. So that's what I wanted to explain. Basically, the derivative doesn't exist. Based on this definition, the derivative doesn't exist at x equals to 6. Okay, so the same explanation that I've used there, we are going to use, let's go to those activities. So this means even at this one, it will be continuous, but because the limit does not exist there, it will not be differentiable at x equals to 1. Okay, so for this one also you have to check that. Okay, so the most important thing was to discuss differentiability and continuity. There's a reason why I'm doing this. Later on under integration, we'll be dealing with this problem like this. We integrate, let's say, from 0 to 1 over x dx. So this thing, it will, because differentiability and integration, these two are related. So a function, if it is discontinuous, you can see here it's discontinuous at x equals to 0. So you cannot integrate this. This integral does not exist. So the mathematician will find a way of determining this type of integral by integrating this type of integral outside this discontinuity. So that's what we'll discuss later when we deal with this mathematics. So the differentiability and the integration, actually they are related because of that, those two things. So as you differentiate the function, you must always think of it, is it differentiable at this point? Okay, so I think I'm going to end my class there. So in our next class, I don't know, I'll check. Maybe we can discuss what we call standard differentiation rules. So we'll start with the power rule that we did in high school and so on. Okay. And now I can take your questions. Let me just try to save this one. It might be important. I don't know.